Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, let's continue our computational fluid dynamics CFD tutorials. In this video, we're going to talk about radial turbines, and we're going to carry out or generate a high quality mesh for a radial turbine design. But before we start, let's take a look on the radial turbine concept or the definition. It is a turbine in which the flow of the working fluid is radial to the shaft. The difference between axial and radial turbines consists in the way the fluid flows through the components, the compressor and turbine. The radial turbine is as similar as the centrifugal compressor, but the function is not the same. Whereas for an axial turbine, the rotor is impacted by the fluid flow. For a radial turbine, the flow is smoothly oriented perpendicular to the rotation axis, and it drives the turbine in the same way water drives a water mill. The result is less mechanical stress and less thermal stress in case of hot working fluids, which enables the radial turbine to be simpler, more robust, and more efficient in a similar power range. Okay, here and when compared to axial turbines, when it comes to high power ranges above 5 megawatts, the radial turbine is no longer competitive. Why? Due to the heavy and expensive rotor, and the efficiency becomes similar to that of the axial turbine. So the research nowadays and the trend of the scientists and the designers and developers is to increase the power extracted from the turbine and to make it not heavy, okay, and to use not expensive materials, and to use materials that can work in the conditions of very high temperatures, because this is very preferable. And here there is a very good lecture that covers the radial turbine aerodynamics and thermodynamics and losses from NPTEL, the Indian Institute. For this professor, it's very important to know this Prof. Bhaskar Roy. And here you can see the design of the compressors or the radial turbines. And here is the radial turbine design. Look, you will find it not airfoils. It is not like the axial turbine. The axial turbine uses airfoil, but here is not airfoil. There is a very complex shape. You know that the turbomachines is one of the most complex systems for the mechanical engineers. And here are many designs of the turbines. Here are radial turbines. And the concept, I think it depends on or it's according to the change of momentum. Here is the inlet, and then changes the direction, so the rotation occurs. For the airfoils, the concept is not the change of momentum. The concept is the delta P, the pressure difference. Okay, here the Turbosystem user guide of Ansys. This is Turbosystem Vista RTD radial turbine design. To generate a high quality mesh for a turbine, a radial turbine, there are two ways. So we're gonna use BladeGen for the automatic design, and then we're gonna use RTD, and then we're gonna complete our tutorial manually, like the centrifugal pump tutorial. New BladeGen, select Radial Turbine, and you have to know Z and R from BladeGen. You'll find it here. Here is the flow path. Okay, and here is the vein and the blades number, the numbers of blades. Okay, in no time we generated the flow path. Here is the inlet and here is the exit. Click on the 3D view. Look, this is the blade and the flow inlet. The flow enters from here, this, and changes its direction and exit from here, like this. Okay, and here is the roller. So the inlet is from here and changes the direction to here. Okay, then after finishing blade design, you can transfer it to TurboGrid to start your mesh. Okay, or let's take a look on the geometry. Okay, you have to click generate. Here, blade body, fluid zone. Okay. And the inclusion and the periodic one and so on. And here is the fluid flow path. As you know, if you want to use Fluent or CFX, especially CFX, if you want to use TurboGrid, you have to generate the flow path around the vein, because we are gonna make the simulation or investigate the flow path, not the blades of the turbine, not the design that was carried out or generated by SolidWorks or CATIA or Inventor. No, we in the CFD CFX or Fluent, we investigate the flow path, not the veins. So here the flow path, and here the design, and click on the meridian plane. You know that this software follows the theory of the meridian, and here this is automatically generated. Okay, here is the inlet and here is the exit. You use BladeGen, no need to open the geometry, just transfer it to TurboGrid. Now we're going to talk about RTD, Radial Turbine design. Let's open Vista. Here is Vista. Everything you need is here for the tabs. Aerodynamics, you can set the operating conditions here, and the efficiencies, everything, and the fluid properties and the flow angles, exit angle, SI units or imperial units. Here the geometry, the impeller, vanes, axial length, the vane roughness, cast finish or mechanical finish, and some more. And here are the results. But before the results, we have to calculate according to these inputs. So you have here is the inlet and here is the outlet, and here input data, summary and the performance, the inlet velocities, the exit velocity at shroud, and so on. And here we can see the velocity triangles in no time. This is the benefit of using this software. So you can change the inputs and see what will happen. Look. Look the changes. So you have to know what's going on. If your input is not logic, the software will tell you that you will get an error message. So you have to change the inputs. Okay, close this and transfer it to create new geometry. To open the geometry to know the concept or the idea of the flow path. Use these softwares, you have software programs, you have to know everything about the inputs. If you have no idea about the inputs, check out the user guide. And if you have your own design that was created by Inventor, Katia, or SolidWorks, it is, I'm gonna show you after a couple of minutes the manual method to generate the flow path, because we will not be able to use BladeGen or Vista RTD because we have no idea about the inputs or the angles or many things. So let's open the geometry. Here is the design. This is the radial turbine according to your input data, and click on the meridian plane, and here is the tricky thing. Contour, shroud contour, and the inlet contour. If you use a compressor, a radial centrifugal compressor, you will find this is the exit, not the inlet. And for the turbines, here is the inlet and here the exit. If this is a compressor, you will find this is the exit and here is the inlet. And here is the flow path is automatically generated. Okay, and for the blades, here everything about the blade like this. There are 4 minutes video about this on YouTube about CAD import feature. You can check it out about the centrifugal compressor. So if you have your own design and you wanna generate a high quality mesh using TurboGrid, and you cannot use BladeGen or RTD, Vista RTD, so you have to generate the flow path manually. So let's talk about it. By the way, you can export these blades from the geometry of Ansys. All this geometry, you can export it as a file. as a parasolid text or parasolid binary or Ansys natural file, IGES, step file, and so on. So if you wanna get a file to open it on SolidWorks or Inventor, you can change it or import it as parasolid binary. Okay. You will be able to open this geometry by SolidWorks or Inventor. And if you wanna import the single blade, you can make this suppress body, drag suppress body, drag them, suppress body, suppress body, suppress body, suppress. And now we have the blade only, and you can export it to open it by SolidWorks or any other CAD design software. Okay, now let's begin our tutorial. We're gonna generate the flow path manually. Let's open a new geometry, and I have a blade. You can work on the blade or you can work with the rotor. If you have your own design on SolidWorks or Inventor, you have to import it into Ansys. Here, open XY, units, make it millimeters. File, import external geometry file. You have to save it as XB, okay, a binary. Okay. SolidWorks can save it as XB, parasolid XB, but Inventor, I think that it has a problem with this extension. You can convert it by Inventor, but you have to open it by SolidWorks and import it or resave it as XB. Let's open it, add frozen. Okay. Then generate. Here is the blade. Notice that the blade or the rotational axis rotates around the axis. Is very important for this. It is not the same as the axial turbine. I showed that in my tutorial. And please, you have to look at the this sign. It has to be green, not yellow. We'll make it at frozen because we're gonna use CFX for the volute, and the assembly and the volute will be add material to use a procedure, the frozen rotor or the setup in CFX. So here, now how can we generate the flow path? First of all, we have to make revolve to revolve the hub and shroud. We cannot make this in SolidWorks or Inventor because you have to make a 3D revolve. We can select here this. Okay. The axis will be XY, plane normal, then generate. And here is the benefit of the revolve tool in Ansys. Now select the hub or the edge. This is the hub. Oh, sorry. Yes. This is the hub. And this is the shroud. So we're gonna slice these bodies. Select by plane. No, select by plane, yes. Slice by plane, not selected, not all bodies. Bodies, this and this. Apply. And we're gonna use the X for the slice. Generate. Now you can use this. Suppress it. Unsuppress all bodies. Suppress this. As you see, we have here, I think that we have to make a roll. So before we make slice like this and this revolve and suppress all bodies. Like this, and I have to be sure of the revolve. Like this. Was tricky. Why? Yes, here is the hub. Yes. Notice you have to choose all the edges and delete this revolve. Here is revolve. Select this and you have to select this too. I did not notice that at the beginning, so it's according to your model or your blade. Okay. Make it fly, generate. Oh, sorry, we have here a problem. So see what will happen. Okay, we choose this and this only, and this is the hub. This is the shroud. Now we can use slice tool. Not all bodies. Bodies this and this. Yes. And the axis, the x-axis, the x-plane, and separate these bodies. So now we have, this is a blade. Okay. We're gonna, here is the XZ. Okay. We have to make a plane in the X on this plane. Right click, insert sketch projection. Okay, it doesn't matter. This and this and this. Okay. So we have here is the shroud contour and here is the hub contour, and we have to draw the inlet and the outlet. So plane, new sketch, sketch 2, constraints. We have to make sure of the auto constraints, check it. Yes. Draw line. Here you can find that you can locate this. We're gonna draw the inlet, the outlet. It's up to you here to use the dimensions. Please be careful. You have to draw the lines carefully. Escape. Delete this. And here. V. Okay. And delete this. And this. Okay. And for the inlet, the same concept. Yes. Make sure that is a horizontal line. Okay. Okay. Please be careful that these points are connected. You'll find this again. Let's remake it. Here is you will find it as a box or a rectangle, and here is the connection. Okay. Now we have to convert this sketch to lines to make it edges, because we cannot select notice that we can select this and this, but we cannot select those. So concept, lines from sketches, and select sketch 2, add material, okay, apply, generate, and so you now look, you can select all these. And now we're gonna generate another plane in the X, generate, and plane 5, okay, insert sketch projection for the hub. I have to select the hub edges. The hub is here from this, and this, and this. This is the hub. Generate, insert sketch projection. Here is the shroud. Okay, this is the shroud. All the signs are green. And the inlet, here is the inlet. And the outlet. I have to generate every one in sketch. And here is the exit or the outlet. Okay, now we're ready to generate the flow path. The flow path machine type is a radial turbine, right-handed, hub contour. So the hub contour, shroud contour, inlet, outlet, generate. Okay, congratulations. Now we generated the flow path manually, like exactly RTD. Here, this flow path is generated automatically, and we this is according to the input, but we do not have these inputs, so we have our own design. This is the outlet, and here is the inlet. Now the most important step is to export points. Okay, but before we export points, we have to select the faces of the blade. Here is the faces. Before this, select this and hide it. To select the faces of blade, we are gonna select this face and this face, and this face, this. Okay, do not select the other faces. Okay, only these faces, and right click, name selection, the blade surface, click apply, the blade surface. Okay, generate an here blade surface and export points. TurboGrid, yes, blade flow path, here the TurboGrid. You can use it mean line. I do not know what the mean line means. And TurboGrid and blade flow path. Click on the flow path. and here the blade number of blades, we're gonna make it 15. Blade row number, it will be one, it's gonna be 1, and the blade surface, click on the blade surface, apply, generate. The gentleman, congratulations, for the second time we exported the points successfully manually. And check out this sign, it must be a green. If it is not a green, if it is red, you have an error, so you have to check out the steps. You did something wrong. And if it is yellow, it's good, but you have to change the offset of the hub and shroud offset, increase it to 0.6, 0.7, 0.8, 0.1, and so on until it gets green. It must be green. Okay, gentlemen, close this and save your work. Okay, you have to save your work. We did it successfully. You can add layers, but I think it may cause problems, so we're gonna transfer it to TurboGrid, and here's the TurboGrid. Notice the units in meters, and process shroud blade passage, and trim blade setup, create passage, and so on. Notice that if you import your design using with the blades and the cover, you have to suppress the cover and suppress anything except the blade to and repeat what I did. Here is the flow path of our own model. So here is the inlet and here is the exit. Two blades, and here all the blades. Looks nice. Just a random example. So I want to check the outline. And here are the blades, and here are the inlet and the outlet. Okay. Right click on topology set, suspend it, and check it to start generating the mesh. If you want to carry out an investigation of the mechanical stresses or on the surface of the blades or something like that, you are not allowed to, or you don't have to make all of these steps, because you will have to carry out the investigation on the blades itself, not the flow. Warning, there is no valid inlet domain to mesh. The inlet domain will be turned off. Okay, this is at the beginning. I'm gonna check it out later. And no errors in the hub or the shroud. Right click, create mesh. And here are the total nodes and total elements. Okay, and here is the mesh. Check all of it. and the outlet, low blade, the outlet, and the shroud. Check all these, not have it. Gentlemen, this is the mesh. To check out the mesh analysis, select this, and you'll find here the bad elements. Yes. The maximum element volume ratio, the value 6.42, and the bad elements percentage is 15.9, and here is the very low percentage. Okay, so how can we improve the quality of the mesh? Open the mesh data, and here we'll find global size factor. Before this, based on what? Here is the tricky. There is a radial turbine thesis here. It is available online. The conceptual design tool for radial turbines. Engineer Elias, I think Michael, I'm not sure, is from Sweden. Okay. I appreciate your work, sir. It's a very good thesis. Contents. Okay. He used the TurboGrid and he did exactly the same steps to generate the flow path manually according to his design. And here's the volute inlet intersection and simplified volute and the theory of the radial turbines, stator, rotor, and volute, and the computational fluid dynamics and Navier-Stokes equations are available. And by the way, you can find a very good course online from NPTEL. I appreciate your work, Indians, for this professor. Week 2, Module 1. You can start with Week 1, Module 1 for the beginners of the CFD, and we will find a lot of information about this course. Structured grid and unstructured grid, the difference between them. Here is the structured grid, and is preferable in these kind of simulations to check out the boundary layer and the high accuracy models. Here is the Navier-Stokes equations, partial differential equations, and here the fluid mesh and the Y plus. Y plus is a factor or a number that determines the first layer thickness. What is the first layer thickness? And the Y plus, let's take a look on airfoil mesh. Here, just an example. This is a vertical axis wind turbine airfoil or an airfoil. To check out or to investigate the boundary layer near the surface of the blade, whatever airfoil or a blade like the radial turbine blade, you have to check out the Y plus number. The number of Y plus is according to the references, and Y plus boundary layer Y plus. The sphere internal flow and external flow. It's available on LEAP Australia Computational Fluid Dynamics website. You can reach it easily. To resolve the viscous sublayer and the boundary layer, there are recommended values for Y plus. If you want to resolve the viscous sublayer, Y plus is order of magnitude 1, and it needs a very, very fine mesh. And this will generate a very big number of elements, and it will take too much time for the computation. And here, adapting a wall function grid, Y plus greater than 11, this is the recommendation. And autonomous models are applicable. Shear stress transport K epsilon with scalable wall functions. This is the recommendation of the solver. And here is the mathematical model. I showed in the previous tutorial of the pumps to investigate or to predict the Y plus. So here the first layer thickness is the first element height from the surface to here. Okay, it has to be calculated accurately. This is unstructured mesh, but you have to this is with a flab. I have a presentation on my YouTube channel about this flab here. Here, this is my presentation about the flab, using the flab and the dependence, the accuracy of the grid. You can check out this presentation, and here is my full tutorial. This is the flab. Here is the unstructured grid, and we have to make the layers here structured to capture the boundary layer according to the computational recommendations. So the Y plus determines the first layer thickness. And what is the sublayer and here boundary layer of the flat plate, laminar boundary layer, and then Reynolds number increases, so it becomes turbulent. And here the viscous sublayer is a very thin layer. If you want to investigate it using CFD, you have to calculate the Y plus, and it's going to be in order of magnitude 1 or lower. Okay, if the Y plus is greater than 1, you cannot investigate this layer using Ansys or any software. Okay, here then he used the structural FEA method to investigate the blades, and here the methodology. And here the design modeler, he carried out the same steps to generate the flow path of his own design, and then used TurboGrid. And here the recommendation of the models and the Y plus. Y plus equal to, and is at the approximately Y plus equal 30. Here hub and shroud, and here the structural meshing is to investigate the body of the blades, not the flow, and he used ISIM CFD. And he carried out mesh independence study. And then the results and the performance and the structural analysis and the mesh statistics, and here are the Y plus. Okay, then he showed the appendix of the steps he carried out at the end of the thesis. Good work, thank you. And here is very good computational methods for fluid dynamics, a very good reference for the beginners in this career, or these investigations. You will find the structured grid and the unstructured grid. The structured grid is good at the simple geometry, or the turbo machines that we're going to investigate the boundary layer or needs a high accuracy mesh. And if the mesh is structured, it will the nodes or the elements will be lower than the unstructured mesh. This is the unstructured mesh, and here is the structured mesh due to the boundary layer, and so on. You can read this reference, very important for you. And here are the basics of coding. Okay, so now we're gonna complete the tutorial. We have to check out the first layer thickness according to Reynolds number. Let's see the hub. This is the hub, and here is the blade. Here Reynolds number I think is not constant due to the design. And here is the first layer thickness. I mean this. Yes. So let's see. Here the first layer thickness approximately 2 0.02 millimeters. It's very small. Okay, so according to what? According to the model, okay, per pumps or any internal flow. This is the same model. Here you have to calculate Reynolds number at the inlet of the turbine. According to your design, you have to calculate Reynolds number, rho v d. D is the characteristic diameter, and v is the velocity, I think, of the gas. and mu is the dynamic viscosity of the gas. So the velocity, suppose that like this, and you have to set rho and mu, and here the characteristic length or the characteristic diameter. It's according to the geometry that the gas will enter, and then it will enter the turbine. So we have to be sure of the diameter and calculate. Here is y plus 2. So make it 30. You'll find that the first layer thickness, it will be 0.00039 meter. Okay. Okay, so it will be 0.39 millimeter. So here we can change the global size factor. If you increase it, the total elements will increase and the first layer thickness will decrease. So we're gonna make it 0.8 and apply to reach 0.39. Check out or make it 0.6. Notice that the first layer thickness increases. We need it lower than 1 millimeter. And here the first layer thickness is approximately 1 or 0.1, and let's increase it, make it 5. Okay, 5. Yes, like that. But here, notice that is not a uniform value, increases and decreases according to the geometry. So you have to make mesh dependency study until you get the required results. Look that the total elements is very low. But notice that the diameter here this is a random diameter and a random calculations. So this is another model. Okay, so it may be not accurate. So let's create the mesh. I just tell you the method. And look at, this is a very high quality mesh with low elements. Okay. Okay. This is the mesh for this design, and these calculations, I'm sorry, it is not accurate and it is not compatible with this design because it's a random design. I have to change the diameter and I have to change the velocity. So just an example, this is a random delta, may works. This mesh may be very good for this model, or it may be very bad. So this is the first layer thickness here. It's lower than 1 millimeter, I think. Yes. So this is good. and we enhanced the mesh statistics. Okay, you can check out the TurboGrid tutorials, or TurboGrid here, roller. We'll find many tutorials here like that. Okay, sorry. Okay, now we can see also that we can add layers, insert layers automatically, or use define object layers automatically. Click apply. You can change the layers, settings, create mesh. Yes. Insert layer, layer after. You can read about layers. Look at the fantastic mesh. So the total elements here is low because this model is small. And here is the layer, very high quality. Also, you can insert many layers. Okay. For the unstructured grids, according to here in a paper on study analysis for impeller volute interaction centrifugal pumps, the researchers used unstructured grid due to the complexity of the model. Okay, so it's up to the researcher and it's up to the model. Now we can close TurboGrid. And I think that we showed right click and update it. This is the mesh. Okay, gentlemen, this is all right. It's very good, and you can now transfer it to CFX, and then you can carry out CFX, no problem. And you can carry out the mesh of the volute and the mesh of the stator, and also transfer it to the same CFX and to carry out your investigation. I hope this well. I hope this works with you well. Wassalamu alaikum wa rahmatullahi ta'ala wa barakatuh.